All right, so let's start. Do you have any questions? All right, so last time we were discussing 3.1, Intro to Linear Systems. With constant coefficients. Also homogeneous. All right, so that's a bunch of words that say that what we're looking at, all right, is something like this. dy over dt is a matrix times y. Okay, where so y, the vector y, is a vector with n dimension. In this class, n is 2 or 3 to be the most common. A, right, is an n by n matrix constant. All right. So to repeat again what we said last time, in terms of notation, I want to emphasize, right? Notation will be heavy, all right, in this materials. So it's very important that you know what object we're looking at. That's one of the features of linear algebra. If you don't know it's a vector, scalar, etc., then it's going to be very hard to understand the context. So when I have something like this with an arrow, that's going to be a vector in Rn. When I have something like this, capital, right, that's going to be a matrix. And usually in this context, we only look at square matrix to begin with. So it's going to be n by n. All right. I mean, matrix in general doesn't have to be n by n, but usually here. And the last notation is y by itself, which is a scalar. Okay, or something in R, something like a real number. Okay. So for that reason, right? For example, I could have written something like this. That let's say y1 of t, right, is c1, let's say e to lambda t plus c2 e to 2 lambda t. y2 of t would be c1, sorry, forget the lambda, right? c1 minus t, let's say. And then let's say 2 e to minus t plus c2 times 3 e to 2t, okay? So in this notation, what I mean, right, is y1, y2 are two scalar, right? Because they are just numbers, right? Of course, they're a function of time, but they're not vectors, right? They're just one single row. This is the first row of the system, second row of the system, right? And each row is a scalar in terms of I mean, a row is not a scalar, right? But what I mean is like the y itself, right? The value of the y itself is a scalar. If I organize things in a different way, if I look at a column, then vector y1 is c1 times 1, 2 e to minus t, okay? And then y2 is c2, 1, 3 e to 2t. So, right, and so here in this context, the vector y1, right, is the first, it's like the first component of the solution. The vector y2 is the second component of the solution, right? And this is after you solve for the system, but before, right, before you have, when you pose a question, you might have something like this, right? dy of t, let's say is, 1, 2, 2, 1 times y of t, sorry, dy dt. So this is the matrix A, right, that we usually refer to. for example. Okay, so I will stick with this notation. I will rarely, I will never, right, should not deviate from this notation. But so do clarify if anything I wrote down don't seem to match with the notation that you expect. Any question on this? All right, so then I prefer not to, Lauren. You can ask me separately, you know, after class or during office hours, whatever. But yeah, I will. I'll discuss. I'll be happy to discuss with you after class if you have time. Yeah. All right. Okay. So continue. So let's see here. What do we want to say, right? One of the important, all right, the important abstract structure, okay, of the solution to y of t, sorry, dy d over dt of y is a times y, okay? So the linear system is this, that when you see this, okay, this is homogeneous, and you will always expect the solution to be like this, c1y1 plus c2y2 plus cnyn, okay, where C1, C2, of course, are undetermined coefficients, you know, just integrating constants, and Y1, right, Y2, Yn are independent solutions to be found. All right, so we discussed the idea of independent last time, so I won't repeat, right? We will explain them where appropriate, but I will not repeat that idea. I will also not repeat the idea of what we mean by a vector, right, in time, vector function in time to be independent of each other. But right, just to recap, the idea is, by the way, right, the reason why there are n solutions is because in the abstract context, I assume that A, right, the dimension, the number of equations is n equations, right? N equations, and A is size n by n, all right? N equations, n unknowns, if you will, right? The unknowns being the rows, okay? So in some sense, it's this n equations, all right, n unknowns. Here's some kind of really a little bit subtle idea. The unknowns here are the y1, y2, up to yn, all right, without the arrows, okay, without the arrows. You understand? So this is like the first row of the solution, serve as the first unknown, second row of the solution, etc. Okay, do not be confused them with this. These are fundamental solution components in exactly the same way as, so these are the unknowns in the system, okay, but the solutions are written like this. Are we okay? So you have n equations and unknowns, and your goal, okay, the goal will always to be find n independent vector solutions like this, and then make an abstract combination of them if we do not have to solve for the initial condition. But of course, if the initial condition is given, then you need to solve for them. Okay. Yeah. Go for it. No. And I think the best thing for me to demonstrate now is, I usually I should give the whole abstract lecture, but I did give it last time. So for now, let me go to, so yes, so Lauren, no, right? You're right, they're not vectors. But for now, let me go straight to 3.2, explain the idea of solutions there, and then I'll go back and demonstrate, okay, the whole structure here with examples. And so you see, okay? So 3.2 is straight line solutions, they call that. Or I like to call this system with real eigenvalues. Real distinct eigenvalues. Okay, I'll explain. So, well, let's take a look at one example, and we'll describe, right? So this is the method, the generic method to solve for the system. So let's see. Let's consider a specific example. Let's say, so this is 3.2, problem 3. They look at dx dt, dy dt to be -5 minus 2 minus 1 minus 4 times xy. Okay, that's the book notation, and that's the book's problem. So to kind of match it with, my notation, the x here is what I call y1. The y here is what I call y2 without the vector. Okay, and so they are also what I refer to as the unknowns. Okay, they are the unknowns, unknown functions. Okay, so now how do we solve for a system like this? So the general approach, okay, and so I will go back to my abstract structure of the equation, which is dy over dt is a times y. Okay, so the general approach is to look for solutions of the form y of t to be a vector times e to lambda t. Okay, v here is a constant vector, meaning v does not depend on time. Okay, but that's the general approach. This should remind you of the characteristic equation that we discussed in the previous chapter. Okay, so here, right, the lambda is the unknown, but v also is the unknown that we need to look for. And what's the motivation? The motivation is when you differentiate with time, right, with t, the form will repeat itself. And so we have a hope to solve for it. But basically, right, if you assume this form, what happens? Then dy dt will be lambda times v e to lambda t. Okay, so pay attention, right? Lambda is a scalar, so it comes down. Okay, e to lambda t also is a scalar. The only vector in here is the vector v. Okay, so scalar. Now, if you are not, very visual in this, what I'm writing is something like this too, if you want. You look for a solution of this form, where v1, v2 are constants. Okay, so v1, v2 here is exactly what I mean by the vector v. All right, and so I hope you see clearly that, right, dy dt is lambda v1 e to lambda t, lambda v2 e to lambda t, which is exactly, right, lambda v1, v2, e to lambda t. Okay. But of course, right, I mean, you see writing the vector down explicitly is very tiring. And if we have like a 10 by 10, you're not going to sit there and write down 10 abstract coordinates. Okay, so that's why this notation is used. So now we plug in, okay? We plug the solution into the system and see what must be the relation between lambda and v. And if you plug in, right, you see that dy dt on the left-hand side is this. So I got lambda v e to lambda t is a, right, times y, which is v e to lambda t. Again, right, one thing that some students are not used to, right, transitioning from, I don't know, calculus to linear algebra and stuff, is the order of multiplication must be respected, okay, at some point, of course. So here, for example, you can switch everything like this around and there's no harm because they're all scalars, right, except for this. So you can switch them however you want. But if you write v times a here, you may think there's no harm done. Actually, it's nonsense, unless you meant your v to be a row, right? But conventionally, v is always a vector. So it's a times v, okay? Things like that. Okay, but after that, right? I did not replace anything, Carl. I plugged in. It's a times y. What's y? So this is the left-hand side. This is right-hand side. Okay. So now, but of course, right, this is a scalar that's non-zero because it's exponential. I can cancel, and I get exactly the relation of lambda and v that I look for, namely this. Repeat what I told Carl. What I said was, right, yeah, I plugged this form, okay, this form of the guess. So basically, you guess the solution to be of this form, which is an exponential scalar, a scalar exponential function in time, multiplied with a constant vector. If you trace the structure, this is the derivative. Then I plug that into the original system that I'm supposed to solve to look for the relation between v and lambda. Okay, and I got this to be the derivative, and this is just a times y. Okay. All right, so after cancellation, I got AV to be lambda v. Okay, any question on this? So also, right, I mean, I think someone mentioned last time, I forgot, but obviously you don't look for zero solution, okay? Zero is a equilibrium solution, right? We remarked last time, we don't look for zero solution. So here, clearly v cannot be zero, the zero vector. Okay, you're not looking for that kind of solution. So this is a relation where v is non-zero. And that's exactly the definition of lambda eigenvalue, eigenvector. Okay, so you say lambda is an eigenvalue corresponding to eigenvector v. Okay, so that's a theory behind everything actually. The rest are just like kind of working out the details in different cases. Okay, so the steps are like this in general. 1, solve for all eigenpairs of A. Okay. Step 2, construct solutions of the form y C1 V1 e to lambda 1t plus C2 V2 e to lambda 2t all the way to CNVN e to lambda nt, like that. So notice, right, these are exactly your y1, vector y1, right? This is your vector y2, vector yn. Okay. So that's it. That's really it. But of course, right, this is more simple than it really is in reality. The reason is, if you recall, first of all, eigenvalues can repeat. If eigenvalues repeat, you may or may not have enough eigenvectors to go around. In other words, you can have repeated eigenvalues with only one eigenvector. What do you do there? Okay, we'll discuss that later. Also, when this is a complex eigenvalue, what do you do there, right? The solution is very similar to the complex, root of the quadratic that we discussed before. You get cosine sign here, okay? Even though it's masked in the, Euler formula of e to something complex number, okay? But in general, this is not wrong. This is the abstract structure of the solution. You just have to reinterpret what this expression means for different cases. So for the simplest case, right, where we have real distinct eigenvalues, okay? So you see what I mean by this title. Distinct meaning I don't have repeated eigenvalues. So I don't run into the issue of not having enough eigenvectors to go around. Real means I don't run to the issue of complex, okay? We'll reserve those for later sections. Then your solutions are straightforwardly this, okay? So we're going to apply this approach to the example that we wrote down right here and show how you do it. Any question? Oh yeah, of course. I mean, A will always be given, as in like, a particular question. Sure. I mean, there could be some abstract theoretical question. If A is this abstract structure, what can you say, blah, 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 right? Oh, you will have to solve for all given lambda. All lambdas. That's the name of the game. You will always have to solve for the lambdas and the V. Yeah. So let's take a look, all right, to this example. So y prime, okay, I'll just write like this, is -5 minus 2 minus 1, 4, I believe, times y. Minus 1, minus 4. Why are they all minuses? I don't understand. Might as well turn them to all pluses. Yeah, who cares? All right. So how do you find eigenvalues, eigenvectors, right? So these are the steps, right? Now your linear algebra knowledge has to come into place. How to solve for eigenvalues, eigenvectors? First, right, solve for eigenvalues by determinant of A minus lambda I is equal to 0. Okay, so you start out working on this equation. You can call that the characteristic equation if you want. Okay, I will explain this, or a refresher of linear algebra, right, after this. But to kind of preserve the flow of the discussion, let's just proceed to see how to solve, right? What's A minus lambda I in this case? If you're used to this, you just write down right away. If you're not used to it, I recommend write down what A minus lambda I look like, because again, some folks may not visualize that correctly. This is A minus lambda I. All right. You okay with this? So you subtract lambda on the diagonal, okay? Then the determinant, right, of A minus lambda I. Here, determinant of 2 by 2 is very easy, right? You always do product like this. So it's going to be 5 plus lambda, 4 plus lambda minus 2, right? It's supposed to be equal to 0. So you see with 2 by 2, you always work with a quadratic, right? That will be lambda square plus 9 lambda plus 18 is equal to 0. So it seems like 6 and 3, right, are solutions. Rather minus 6 and minus 3, that's what I mean. Are we okay here? Okay. So then you solve for eigenvectors. By plug in, right? And solve a minus lambda I v to be 0. Okay. Plug what in? Plug the eigenvalue you just solved in. Okay. One remark. Okay. The eigenvalue, the eigenvector will not be unique. Okay. I mean, v is not unique. All right. Do we know why? Yeah, multiplicity or, right? Nothing with distinct eigenvalues, Carl. This is a homogeneous system, right? This is a homogeneous system. And remember what we said last time. When does a homogeneous system have a non-zero solution? When the determinant of this is equal to 0. That's why you solve for this equal to 0. Okay, you enforce, right, it to have a non-zero solution. But yeah, I think maybe Will refers to linearity, maybe that if this is a solution, then any constant multiple of it is going to be a solution too by linearity. So that's why you don't have a unique solution. But in general, right, the unique solution here would be, if you have any, will be 0. But if you have a unique solution, that implies this matrix invertible. So the fact that you work the lambda so that you make this not invertible automatically land you on a non-uniqueness solution, okay, context. Because 0 is always a solution to homogeneous system. Any non-zero solution automatically land you on a non-uniqueness context, okay, from linear algebra point of view. So if it's not unique, right, then the trick is do not work too hard to solve, quote, like you are taught in linear algebra. A guessing solution is fine. Okay. The trick is you must have enough eigenvectors to go around. So here, right, you know, eventually you have to master your situation. Okay. Here, because it's distinct eigenvalues, each eigenvalue has one single eigenvector only. So only guess one solution is enough. Each eigenvalue only has one independent eigenvector. That's why, okay, guessing one solution is enough. So let me demonstrate, all right? So let's say lambda equals to -3. Plug in, what do we get? We get -8, no, right? Not -8, -2, -2, -1, -1. And if you're experienced, right, sometimes people make mistake here, you know, algebraic mistake, calculation mistake, error, whatever. You will know you make a mistake right away when you look at a system. Because again, right, if you solve it correctly, your system must be dependent, okay, must be non-invertible. So the fact that the top row is a multiple, second row, whatever, is exactly a sign that you solve it right. Okay. So if you want, you can write this down. Okay. But a guess is enough. So I'll do something like this, right? Lambda 1 is -3. A guess or a candidate solution is enough. One solution is -1, 1. Okay, that's all I need. Now let's say that Carl came up with exotic choice, minus pi pi. His choice is fine as well, okay? Because eventually they'll be washed out by the constant multiply in front of them. But, right, when you guess solution or when you have to choose a solution, the simplest form will always make it easier for you to work down the road. But this demonstrates the point that there's no unique choice here. You and your friend may come up with different solutions, right, for all we know. Okay, but of course, I mean, in a simple case like this, actually here, right, maybe the more common difference will be something like this. But again, right, that's perfectly fine because, you know, it's just a -1 times first one. So all of these are okay choices, okay? But of course, you should just go for these two in this case. Any question? So lambda 2 equals to -6, I believe. And so the matrix will be, it usually is obvious, well, and the trick is actually, you know, the trick is to know how many you're looking for, okay? And you just can really blindly just plug numbers in. For example, because you know they must have a solution. You plug in, let's say, the first one to be 1, then you solve for the second. Then the equation must automatically be consistent for the second row because, you know, it's degenerate. The top row and the second row say the same thing. So worst come to worst, and usually it happens a lot. Plugging points works. Okay, lambda equals to -6. Then you get 1 minus 2 and -1 and 2. Okay, so you see the obvious choice for V2 is two and 1, right? Okay, so the final answer is y of t is C1, 1 minus 1, eta minus 3t, C2, 2, 1, eta minus 6t. Any question? Well, anything that works, all right? For both vectors, actually. For example, right, like any of this would work. But of course, I mean, if you pick the wrong choice, I don't know. If you pick V1 to be, if you pick V1 to be here, to be 0, 1, then of course that's wrong, right? That doesn't work. Yes, C1, C2 would be determined by initial condition. And after you resolve the initial condition, then your solution and your friend's solution will be the same. Okay? If you choose different vectors, your C1, C2 will be different. Yes, for the initial condition, correct. But after you settle that, then your solutions are the same because of uniqueness. All right, you have uniqueness here. So prior to that, right, the form might look different. For example, right, another choice here would be C1 minus 1, eta minus 3t plus C2 4, 2 to minus 6t. Okay. Either one is fine prior to initial condition. Daniel, yes, this is so. Of course, the method here doesn't work when the matrix A depends on time. That's the much more hairy system that I don't think we even discuss in this class at all. Yeah. Any other question? So I still don't understand what you mean by offset by different vectors, Albers. What I mean is when you have the initial condition, right? This and this and this and this are not the same for the same initial condition. But after you resolve it, then your y will be the same. Okay. We can do an example real quick to show you that too. Any other question? So let's clarify, right, from up top, where I talk about the abstract structure of the solutions, right? And I mean the y without the vector. So let me clarify that here, okay? So here, right, my y1, I think you've seen it already, is 1 minus 1 e to minus 3t. My y2 would be 2, 1 e to minus 6t. Okay. My y1 will be c1 e to minus 3t plus 2c2 e to minus 6t. Or rather, right, this is x. This is the x that the book's looking for. My y2, or the book called the y, will be c1 e to minus 3t, sorry, minus, right, plus c2 e to minus 6t, where I was using the top form to write that down. Any question? There. I'm looking at top row, right? Usually we slice it through the columns, but of course, don't forget that the solution. Oh yeah. No, absolutely. But you know, again, right? You should usually, conventionally, people do this, but don't forget where this comes from, right? This could come from like a spring mass system, where the first coordinate is a position, and the second coordinate is the vector, is the velocity, right? So in that sense, keeping that in vector forms don't have physical meaning. You have to resolve it back to its position and its velocity, okay? Or, you know, these are, they call the coordinates of the solutions. So you really have to look at the context to see which format, right, is the right one to use. I mean, of course, as far as we're concerned, I don't care, right? This is as good as this mathematically, but physically, right? Which object are we looking at? And so you yourself have to be, you know, the judge of that. All right. Any question? Any other question? All right. So let's just spend 1 minute, right, trying to look at the initial condition, and to show you how, right, different forms resolve in the same condition. Let's just say that the initial condition is y of 0, right, is, I don't know, 1, 1. I don't know if it's hard or easy. Okay, 1, 1. So what does that mean, right? So let's pick the top form first, okay? Top form would be C1 times 1 minus 1 plus C2 times 2, 1 is equal to 1, 1. Okay. So here, right, you just use your, knowledge in linear system to solve it however you want. If the system is not too hard, then you just do, straightforward thing. So here, right, you got C2 is 2/3, and then so C1 is going to be minus 1/3, right? Okay. If I were to use the bottom form, this one, right? Again, the bottom form is just you choose a different eigenvectors. You choose a different eigenvectors. Then it's going to be, right, C1 times minus 1, 1 plus C2 times 4, 2, right, is 1, 1. So what do we get, right? We get minus C1 plus 4C2 is 1. C1 plus 2C2 is 1. So here you got C2 to be 2/6, which is 1/3. And then C1 is, what is it, right? 1/3. But you see, it makes perfect sense, right? Because this eigenvector is double. Sorry, this is the double of this. So the C2 solution in the second form, right, is half of the first form to make up for it. No, Will, if you add them up, right, you got 2, 6, so 2/6. Yeah. Again, right, it should be exactly half of this. And then C1, right, is the negative because the eigenvector is just swap the negative. Right. So of course, if you add them up, they're exactly the same. So that's what I mean by everything get resolved with the initial condition. Any question? Well, in a one eigenvector case, yes. In the one eigenvector case, yes. All right, meaning like when you have distinct eigenvalues, sure. The fun starts when you get repeated eigenvalues. Then people will tend to guess different ones. Okay, but if it's just one, then of course, right? The vector space, the eigenspace of that particular eigenvalue is one dimension. So whatever you guess, right, by definition, is multiple of each other. Yeah, of course. But again, right, that's too simple. Okay, that's too simple. The fun, right, the situation gets much more interesting. Here, right. By the way, right, so this is going to get into some new context. That is like the book only does 2x2, okay, system throughout. My requirement is you will get 3x3 system on the exam, okay, up to 3x3. So you need to handle 3x3 system for eigenvalues, eigenvectors. All right, I'll work some of them out in the class for you, but I think 2x2 is too easy in terms of like it wash out a lot of linear algebra structure. So yeah, right. You need to be responsible to know how to do eigenvalues, eigenvectors for 3x3 matrices. For that I posted okay a file for like 6 matrices 3x3 for you to practice on eigenvalues, eigenvectors on this week's module. So if you want to practice, you can work on those matrices yourself. But right, you need to be able to handle right up to 3x3 matrix. So for that, right, let's just like take a look at one easy example first, and we'll do a more complex example down the road. Let's do this. Okay, this. All right, so you proceed by finding eigenpairs, right? Eigenvalues. What are the eigenvalues here? Yeah, so I purposefully chose a very easy system where the eigenvalues can be read off from the diagonal. Okay. How so? Because this matrix is something called a triangular matrix, right? Triangular meaning, right, either the top half or the bottom halves are all zeros. So I think they call this lower triangular. It doesn't matter. But why is it, right, that is triangular? Then, you know, eigenvalues can be read off right from the you know, the diagonal entries. Is something useful to know. Okay. The reason is, right, what is a minus lambda I? 1 minus lambda 0 0, 2 1 minus lambda 0, 1 3 2 minus lambda, right? And so how to find determinant of a 3 by 3 or higher, right? You do that right, by expanding along a rows or along a column, right? So you expand along a row, you obviously pick the ones that with the most zeros. And so you do, let's say, the first row, plus minus plus. Actually, this doesn't matter, right? So if you expand along the first row, the top row, you got, right, 1 minus lambda, right, times the determinant of this, right, times the determinant of this. But the determinant of this, you see, is by the, you know, 2 by 2 is exactly 1 minus lambda times 2 minus lambda. So it's exactly right there, 1, 1, and 2. Okay. Or in general, you know, determinant, right? Exactly. Determinant of a triangular matrix is the product of the diagonal entries, right? Because of exactly because of this reason, you go down, the zeros always kind of cancel things out for you until the end. Okay. So now let's see the eigenvectors. Okay, let's see the eigenvectors. Any question here? Well, you know, depends on my mood. If I'm in a good mood, who knows, right? You might get lucky. But yeah, in general, you should be able to handle, you know, generic 3 by 3 matrix. Yeah, which we'll do later. I'll give you an example of that. Yeah. So eigenvectors. Okay. So you have, technically speaking, you have 3 eigenvectors, right? But this is a case where I say it's repeating. Okay. But this repeating is not hard, because if you plug in, you get 0 0 0, 2 0 0, 1 1 3 1. So right off the bat, right, linear algebra knowledge, how many eigenvectors do I get here? Solve for this, right, times v equal to 0. Yep, 1. And you know that because where does the 1 come from, Ron? Yeah, it's already reduced, actually, right? It's already reduced. So how, remember the concept of free variable? How many free variable do you have here? Yeah, rank, exactly. The rank here is 2, right? The rank is 2, or the number of free variable is only 1, because you only have 1 row of 0. 1 row of 0, right? So you only expect 1 eigenvector here, okay? And what is that eigenvector? Anyone care to guess? minus 6. What does that mean? Yeah, value of what? Yeah, 0 minus 1, 3 works. Okay, and why do we see that? Because you see this, the second equation says, right, the first coordinate must be 0. The first coordinate must be 0, and so cancel that out. This and this, you just have to guess. So minus 1 and 3 will be it. Okay. But of course, right, another one would be something like 0 minus 2 and 6, for example, right? Any question here? So actually, I said it wrong, all right? This is the hard case, which we'll talk about later, but I'll explain why it's hard. So then the second one is lambda equals to 2, right? Minus 1 because, so again, right, that this is going to be 0, right? The top coordinate could be 0 because 2 times it is equal to 0. So if it's 0, then it zero this out on the third equation. You got 3 times this plus 1 times that, right? So one choice is minus 1 and 3 to get equal to 0. Are you okay here? I mean, some of you may not be that fluent with linear algebra. If you want me to do it in more details, feel free to speak up. All right, don't feel shy. I mean, I do this for like, you know, too many years now, so it's very clear to me. But anything you want me to spell out in more details. Oh, I'll do it later. Yeah. Well, I'm just waiting for folks to clarify if they need questions. They have questions on lambda equals to 1. Lambda equals 2, you don't need to. The reason is, you know, there's only one eigenvector. So no need for elimination. Yeah, I'll show you that. Okay, so lambda equals to 2. What is the system, right? Minus 1, 0, 0. 2 minus 1, 0. 1, 3 minus 1. Okay. So actually, hold on. Did I do it right? Yeah, the last entry should be 0. Otherwise, yeah, exactly. I was feeling weird. Cool, thank you. All right, very good. So what is the solution here? What is a solution here? Actually, it's quite obvious too, right? What must the first coordinate be? And by the way, Will, right, this already reduced for you, actually, right? It's just reduced in inverted form in some way. But 0, 0, and whatever you want. So 1 would work. Exactly. Okay. So any question here? Now, let me say, right, but this 0, because look at the first equation. The first equation says this is equal to 0, right? So it must be 0 here. Oh yeah, sorry, right? That's what I'm saying. I'm so used to this that I don't even care to write the redundant stuff out. But yeah, you always do the right side equal to 0. You always do the right side equal to 0. Yeah. So this is equal to 0. So the first coordinate is 0. Plug that in, kill this. That must be 0. Plug those two in, kill this. but then that can be whatever it wants. So that's why I think Albors, right, said 0, 0, anything. Yeah, so again, you see, if when efficiency is the case, you don't even bother writing this because this is the matrix you're looking at, and you just eyeball it, right, to make it equal to 0. Yeah, I usually call it the eyeballing technique. That's all you do, really. Okay. Any question here? So far, right, all I was discussing is really a linear algebra technique, linear algebra exercise. You're looking for eigenvalues, eigenvectors, which I hope, right, is a refresher, and it should be a routine. But in terms of ODEs, okay, differential equation, then we are in deep trouble here. Why? Because remember, the fundamental structure is y is C1y1 plus C2y2 plus C3y3. But, right, if you look at lambda equals to 1, exactly because it's repeated, right? This is the degenerate case I was talking about. Because it's repeated, you're missing out on one eigenvalue. Sorry, you're missing out on one eigenvector, okay? So using this or using this, right, don't matter. They're the same vector. So that will give you, let's say, C1y1. Using this and this give you C2y2. But you don't have the C3y3, okay? And so that's exactly the topic of discussion for the chapter on repeated eigenvalue proper, okay? So here, right, to be continued is to be discussed later. But as of right now, right, we do not have enough to construct 3 solutions, okay, for this system. All right, you only have 2 solutions, and you see why this is not enough, because you cannot solve for all initial conditions with only 2 degrees of freedom. You understand? Right? With 2 degrees of freedom, you cannot solve for all initial conditions. And I think I tried to, someone asked the question, and I think it's wrong, right? Why 3, for example, here? This is the reason. If you only have 2, right, there was one section we skipped last time, not last time, we skipped one section called existence and uniqueness in multidimensional case. Basically, it just tells you the conditions for existence and uniqueness. For our linear system, there's always existence, okay? For any initial condition, you can be guaranteed on that. But so for that reason, right, that for any initial condition, you must have a solution. But if you structure your solution this way, then you can find initial condition that you cannot solve for C1, C2, right? Because this is only 2 vectors. So that from that consideration, because every initial condition must be able to solve, you need a 3rd vector to help you to do so. So that's the generic structure that we don't have enough to construct right now. Okay, so I just want to highlight this point as a so for what you need to follow, right? No, Albors, it's not like that. This is the case where I think if you take advanced linear algebra, this is called a nilpotent matrix. It has something with nilpotency. The matrix is not diagonalizable, right? What happens is this matrix is not diagonalizable. It doesn't have enough eigenvectors. It only has Jordan form, that kind of stuff. Again, a lot of this may not mean anything to you, right? That's more advanced linear algebra context, like 350. But if you know what I'm talking about, then that's a problem. It's not about null space and that kind of thing. Yeah. So all right, but from your point of view, okay, all I require you to know is how to solve for eigenvalues, eigenvectors, which I hope is straightforward. Okay. Now, what I want to do is to tweak this example, right? Because folks kind of ask about, right? Or I don't want you to get the impression that somehow eigenvectors are always multiple of each other. Okay. So let's tweak this example to this to show you the case that even if it's repeated eigenvalue is fine. Is this. 1 0 0 0 1 0 1, what was it, 1 3 2. Okay, like this. Okay, so I changed my matrix slightly. Okay, right here, this entry. So again, right, what are the eigenvalues? 1, 1, and 2, right? Because it's still upper triangular. What are the eigenvectors? When lambda equals to 1, what's the matrix? 0 0 0 0 0 0 1 3 1. Now, how many eigenvectors do we have here? Two, right? Because you have 2 degrees of freedom, right? You have 2 degrees of freedom, okay? And this is exactly here, right? Your friend and your choice may not be anything like each other, okay? So I'll nominate 2 of mine, right? And you can nominate yours. But I think the most straightforward choice will be this and this, right? Now, does someone care to nominate 2 other choices? By the way, right, your 2 eigenvectors must be independent from each other, okay? For example, if you nominate your choices to be like this, then this and this are invalid, okay? Invalid, because they're the same vectors, okay? This and this are good choice. So yeah, I think correct. So let's take Suresh and Alexander's choices will be, let's see here. -1, 1, -2. Let's see, I want to make sure it works, right? Does that work? -1, -2 is -3, perfect. And then let's see Alexander. Yeah, you zero out the second one, perfect. -1, 0, sorry. 1, yeah, you're right. Yep, very good. Okay, and then, right, you see there are a bunch of combinations, right? And so, yeah, Ron also said the same choice. So you see again, right here, the pair, right, will be the ones, right? These pairs are the basis vectors of the eigenspace. So you and your friend will just go have fun, right, with your basis, and there's no multiple of each other in this case, right? Unless somehow you happen to be exactly on the same basis, then sure, right, multiple, but otherwise, okay? This is what I want to say. And then, any question here? And then when lambda equals to 2, right? When lambda equals to 2, you got 1 0 0 0 1 0 1 3 0. 1 3 minus 1. 1 second. Wait, what am I saying? I think I say something nonsense, right? Sorry. -1, -1, and then 0, right? Yeah, -1, -1, and 0. Sagar, what you do, right, is if you want, they're all solutions to this. V1 plus 3V2 plus V3 equal to 0. And you just play with the combinations that work. So for example, this is one combination that works. This is another combination that works. 2 more. The point is that when you structure them into vectors, they must be independent. So that's it. However you want to pick them. All right. So here, right, I think it's clear that our V3, right, will be, let's say 0, 0, and 1. So your solution Y, right, will be C1, whatever choice you want to pick, right? I'll pick the bottom choice in favor of the class. So that's e to the t plus C2 minus, oh, sorry, the class chose minus 1, 1, and 2. And then minus 1, 1, minus 2, sorry. And then minus 1, 0, 1. And then eta 2t. Okay, so that's your solution here, as before. So here, right, even though you have repeated eigenvalues, the situation is very normal. So you just do whatever you're supposed to from the structure of the solution. Any question here? So right, to be precise, the key, right, or the topic of this section should not really be real eigenvalues, because eigenvalue is 2, right? Am I wrong? Yeah. These are eigenvalues 1, right? These are eigenvectors correspond to that. This is eigenvalue 2. This is eigenvector correspond to that. Yeah. So the discussion here, right, should be more properly called system with full set of eigenvectors. Okay, is the discussion. And of course, you want real eigenvalues because we're not dealing with complex. But the issue, whether it's repeating or not, is not really the issue here. All right, because in those of you who might have heard of this, when we say repeat eigenvalues, we tend to refer to the algebraic multiplicity, meaning the multiplicity when you solve for the equation, determinant of A minus lambda I equal to 0. What really matters is the geometric multiplicity of the eigenvalue. In other words, how many eigenvectors, right, it really has. So if the geometric multiplicity is fine, meaning that it has enough eigenvectors, then you don't care, right? The solution is always the same. So for that, right, the repeating, right, it is really about whether or not the number of eigenvectors you have enough to construct your solution. All right. Any question? All right. So lastly, right, I want to do a example, right, of a 3x3 where you don't necessarily have, right, the triangular structure. So this. Okay. So what do we do here, right? So here, there's no obvious thing to do. You want to find the equation of determinant of A minus lambda I equal to 0. And you might as well pick, anything, any row. So what's A minus lambda I, right? It's 1 minus lambda minus 1, 4, 3, 2 minus lambda minus 1, 2, 1 minus 1 minus lambda. Okay. So I will just go along the first row, for example. So remember, it's plus minus plus, right? So that will be 1 minus lambda times 2 minus lambda times 1 plus lambda. This is minus 1, so plus 1. And then minus becomes plus, right? Plus, okay. Then you got this times this. So that will be 3 times 1 plus lambda. Oh, sorry, what am I doing? I think I did it wrong. Minus 3 times 1 plus lambda, and then minus 2 becomes a plus 2. Let's see if I did something wrong here, sorry. So if I do 2 minus lambda times this, it should be lambda minus 2. Okay, so 1 minus lambda times this, which is lambda minus 2 times 1 plus lambda plus 1. And then this, right, first is minus 3 times 1 plus lambda, and then minus 2 becomes a plus 2. And finally, right, plus minus plus. So that's last one you have 4. 4 you have, right, 3, right, and then minus. So rather becomes plus 2 lambda minus 2 times 2. Okay. So that's usually the name of the game, that you have to kind of simplify this left-hand side in a way and make it equal to 0. All right. Usually the system that is presented to, that the equation is presented to you, have some structure that makes it easy to simplify, and you just have to look for it. Because, you know, this matrix always have nice solution. But right, this is kind of like the polynomial that you will see when you expand out this determinant. All right, it might seem scary at first, but trust me, it's not that hard to work with. And this is as you know, I don't know, as bad as it can get for your exam, right? But you're required to do something like this. Any question on this so far? Now we'll simplify this, right, and solve for lambda. But okay, so let's see what we have. So we have 1 minus lambda, right? And then we got, let's say, lambda square, right? Lambda square minus 2 lambda plus lambda is minus lambda, right? Minus 2 is going to becomes a plus 1, a minus 1. Okay. This, right, is minus 3 lambda. Right, minus 3 is minus 1. And then finally, right, this term is, let's see here, right, 3 plus 2 lambda minus 4. So this is going to be plus 4 times 2 lambda plus 1. 2 lambda minus 1. Okay. So again, right, here, you got to be super careful, and this is where my weak point is. If you make any arithmetic error here, it will cascade down and you will not see the nice solution. So that's the only annoying fact of the annoying part here, that you want to make sure that your arithmetic is right, Because otherwise you won't see the nice cancellation or something that's meant to happen right down the road. So I want to make sure that I got everything right. Okay. So next, let's see here, right? I think this doesn't factor, so let's just keep it for now. I can simplify this, right, to give me, this is 8 lambda, so 5 lambda. And then minus 4 minus 5. And there, you see, this is exactly the nice, I don't know, structure, right? That's meant to happen somewhere in this thing. Again, right, what's the worst case scenario? The worst case scenario, you got a cubic, and you just have to, you know, guess a root, do a count thing. But usually, right, you don't have to work down to a cubic level, okay? Because somewhere along the lines, you will see a hidden common factor somewhere, okay? So you need to look for those. That's why I did not just, charge in and how to say this, expand the whole thing, because, I would slowly simplify and look to see if I have some common factor that help me, okay? And so finally, right, I will factor out, let's say so this is plus, right, 5, rather, if I want, let's do minus 5 times, right, 1 minus lambda, okay? So I'll get, right, 1 minus lambda times lambda squared minus lambda minus 6. And this is pretty simple, right? Lambda equals to 1. I think this is plus 3 plus, hold on, minus 6 is what? Minus 3 plus 2, right? Minus 3 plus 2. So lambda equals to 3 and lambda equals to minus 2. Am I right? Yeah. Are we okay here? This so far is the hardest thing, if you will, right? About a 3x3 system you have to deal with. Mohammed, no, you have a very good question, and you like to think of something like that. That's nice. Except if you do a row operation, you mess up the eigenvalues. Eigenvalues are not preserved in row reduction. The point is, this is a system you're dealing with. You cannot do row reduction to make it easy for you because the eigenvalues are not preserved. Okay, so no, good thinking, but that's not appropriate here. Yeah, I mean, so for some other purposes, like solving for things that equal to 0, right? Yes, right. No, your thinking is very mathematical. That's good, right? You try to simplify the system somehow. But right, when you simplify the system, you better make sure that what you're looking for is the same thing. If through your action, what you're looking for changed, then you cannot claim that, right? You're looking for the same thing. Yeah. All right, any question here? So, okay, so again, practice on this if you need to, because again, I believe that, right, you should be able to kind of expand your vision to 3x3 when it comes to this calculation. Now, right, if you want to solve for the eigenvectors, it's pretty straightforward. 0, minus 1, 4, 3, 1, minus 1, 2, 1, minus 2. All right. So yeah, someone I think Will, right, asked how do you solve for this, right? Yeah, how do you solve for this? How do you solve for this equal to 0? Again, right, I claim that eyeballing might work, but let's see. So first of all, right, you have one free variable. You know that because these are 3 eigenvalues. Each eigenvalue will only have one eigenvector. That means that this system has a free variable. Okay, this system has a free variable. So you can choose, like, let's say, I don't know, the first coordinate to be 1, for example, and solve for the other 2, right? That will always work because you can choose whatever the first coordinate be and solve for the other 2. So I'm trying to think. Yeah, you definitely don't need to do that here. Just give me one moment. So sorry, I'm blanking out. Does anyone see a solution here? Or did I do it right? Did I make a mistake somewhere here? Minus 141. Yeah, I was thinking exactly it's 4 and 1 here, but somehow I just don't believe that these come out to be the same. That's why I saw a 4 1 there, and then I'm like, somehow this doesn't, and I don't trust my intuition. Yeah, thank you, Sarah. Exactly. I see a 4 1 here, right here already, but somehow I just don't trust my intuition. Yeah. Okay, thanks. Right, and then so on and so forth with lambda equals to 3 and lambda equals to -2. I'll let you figure it out. But yeah. Okay, I think it's a good place to stop here. We'll pick up next time. Any question? Any last minute question? All right, so what do I want to say here? I'll stay behind if you have questions on the quiz. If not, then see you next week. Okay. Yeah, you too. Thank you. Yeah, thank you. Okay, Lauren, what question do you have for the quiz? Are you still there?